Hello everybody, welcome to this session. Today we are going to discuss regarding the groundwater hydrology. So in this unit number 4 we are going to discuss regarding the groundwater and related aspects and how the groundwater flow uh, works and how it can be determined by the various formulas or various scientists has given their formulations. We are going to see all those formulations. So before that, it is also necessary to know the various terminologies which are associated with the groundwater hydrology, that how the groundwater gets stored below the earth surface, how it is get stored in the various locations. So all these things are necessary. Also there are various types of water tables are also, so we'll have to understand what type of water table is there, or what type of ground is available there. So all these things are necessary to understand in the groundwater hydrology. So important to start with that what is groundwater. Groundwater is water located beneath the earth's surface in soil pore spaces and in the fractures of the rock formations. So it is when the in the rainy season, when water get percolated in the ground, that goes in the ground and it gets stored in the various pores of the water, and that water is called as a groundwater. And the rest water that flows on the surface of the earth as in terms of or in the form of runoff. The depth at which soil pore spaces or fractures and voids in the rock become completely saturated with water is called as a water table. So here it is a very good picture has been shown here how the water gets stored. Here a cross section of a ground has been shown, right? The precipitation takes place, the water that goes percolated into the ground, the race water that flows on the surface of the earth, and the water that flows through the in the ground, it passes through the various layers. You can see here, you can find the various types of layers are there. Not only that, the water gets stored at the various location. Okay, you can see here the separate water is stored here, and which is associated with this with open well, right? Again you can see this water table, it is saturated, or you can see it is stored between these two layers. Okay, deep water which is in the impervious rock, or in this particular figure in the impervious rock or limestone has been shown here. So this is a deep well, right? So water table, it is not a constant, remember, that may be located at the different locations. Subsurface water. Water in a soil mantle is called as a subsurface water. Water beneath the surface can essentially be divided into two zones. The unsaturated zone, also known as zone of aeration, which includes soil water zone, and the zone of saturation, which includes groundwater. So you can see in this picture how the subsurface water can be located. So on the top side you can see this is a unsaturated land is there where the water is not present, but as the water goes down, you can find the water table here. Also it is associated with the surface water. So saturated zone is shown here where the water is fully available without any pores in the soil structure. Sometimes, essentially during times of high rainfall, the pore spaces are filled with water. The water table divides the zone of aeration from the zone of saturation. In saturation zone, all the pores of soil are filled with water. The aeration zone in the aeration zone, the soil pores are partially saturated with water. So in this figure you can see two zones have been shown here. Immediately to the ground level, zone of aeration is there, where the air spaces or air voids can be found between the various particles of the soil. On the contrary, the particles which are present in the zone of saturation, where all these voids are filled with the water. You can observe the water table here. Okay, here it is written here, unlike the aeration zone, all pores in the saturation zone are filled with the water. So there is no air found in the saturation zone. The aeration zone has three subzones: soil water zone, intermediate zone, and capillary fringe. So here in the aeration zone also there are three parts. Okay, so you can see here also zone of saturation is shown here, there. Then second one is the intermediate zone, or you can see it is a here associated with the capillary fringe. Okay, so that we will see. And also it is a top side zone which is near to the surface of the earth. It is called a vadose zone. Let's have the glance on the soil water zone. Soil water is held in the pore spaces between the particles of soil. Soil water is the water that is immediately available to the plants. This water can be removed by air drying or by plant absorption, but cannot be removed by gravity. Plant extract this water through their roots until the soil capillary force, that is force holding the water to the particle, is equal to the extractive force of the plant root. At this point, the plant cannot pull water from the plant rooting zone and it wilts, called the wilting point. The amount of water held in the soil after excess water has drained is called the filled capacity of soil. So here you understand 2 points here. One is the filled capacity and other is the wilting point. So as stated here, the plant cannot pull the water from the plant rooting zone and it wilts, that it is called as a wilting point. And the amount of water which is held in the soil after excess water has been drained. So water left it is called as a filled capacity of the soil. So for different soils, this wilting point and the filled capacity, these are different, right? So filled capacity is always greater than the wilting point of that particular soil. So here you can see a graph has been shown for the different types of soil, where types of soils have been shown here, and the centimeter of water per meter depth of the soil, that has been shown in terms of the filled capacity. So the line which is in the blue color, you can find it for the filled capacity, which is above the wilting point. Line which is in the red color, which you joining. So for the sand, you can say find the wilting filled capacity is less. On the contrary, where the cohesive forces are there in the clay soil, the filled capacity is more. Now we have to also discuss on the intermediate zone. So this is the layer that is available next to the soil water zone. It lies between the soil water zone and capillary zone. So the cross section is shown here about different for these different zones. So at the bottom you can find saturation zone. Above that capillary fringe is there, capillary fringe. Then you can find this intermediate zone, and above that you can find out the soil water zone. So between the soil water zone and the capillary zone, you can find out this intermediate zone. And also two parts have been shown here, from the capillary fringe to the land surface. It is a zone of aeration where the possibility of the air you can find out, and below the capillary fringe totally saturation zone is there, and which is you can see which is there is no scope for the air, remember, it is totally saturated. Then let's see regarding the capillary zone. So in the picture you can find here near to the this subsurface water, this particular vadose zone is present, and between this vadose zone and this zone of saturation, between that the capillary fringe is there, and the water table acts there, right, and the floor of ground floor have been shown here. So this capillary fringe is the subsurface layer in which the groundwater seeps up from the water table by capillary action to fill the pores. Okay, so in between the saturated zone and this unsaturated zone, right? So if the water is trying to fill up the gaps of the soil surface, soil voids, you can say. So due to capillary action, pores at the base of the capillary fringe are filled with the water due to tension saturation. This saturated portion of the capillary fringe is less than total capillary rise because of the presence of mix in pore size. If the pore size is small and relatively uniform, it is possible that soils can be completely saturated with water for several feet above the water table. Alternatively, the saturated portion will extend only a few inches above the water table when pore size is large. So you can see that depends upon the pore size. So here again you can see if the pore size is small and relatively uniform, it is possible that the soil can be completely saturated with the water for a several feet above the water table. And if the pore size is small, so above the water table the saturated portion will extend only with a few inches above the if the voids are more. So you can see here also these two particular figures. So in the top portion the vadose zone is shown here, and the infiltration, that how the water goes in and how the evapotranspiration takes place. So in the saturated zone you can see the capillary rise is found, where water will try to move from the saturated zone towards a little bit dried zone, or try to occupy the various pores, and this capillary fringe present between these two layers, right. This is the water table, the groundwater flow is shown there, and this capillary rise, or you can say the saturated portion, that depends upon the pore size of the particles, or you can say between the particles. Now saturated zone is also classified into four categories. One is the aquifer, aquiclude, aquifuse and aquitard. So this particular figure shows how these layers are present in the saturated zone. So initially it starts with the aquitard, the water table is present, and then you can find the aquifer, and what is next is the aquitard. So what is the meaning of this? We'll see one by one. Now first one is the aquifer. An aquifer is the layer of porous substrate that contains and transmits the groundwater. So from the aquifer the transmission of the groundwater takes place. An aquifer is an underground layer of water bearing permeable rock or unconsolidated materials, gravel, sand or silt, from which groundwater can be extracted using a water well. Okay, so from the aquifer the water can be extracted. Aquifer may occur at various depths. So you can see find out this particular figure is shown there, how the water is extracted from a aquifer. So this is the total aquifer is shown here, right? Now there again we'll have to see the types of aquifer. First one is the unconfined aquifer. Unconfined aquifers are sometimes also called water table or phreatic aquifers because their upper boundary is the water table. Okay, so unconfined aquifer you can find here, and this is what we are seeing. This particular is the water table. So upper surface of that is the water table. When water can flow directly between the surface and the saturated zone of an aquifer, the aquifer is unconfined. The deeper parts of unconfined aquifers are usually more saturated since gravity causes water to flow downwards. So again you can see this unconfined aquifer followed by the aquitard, and again followed by the confined aquifer, and below that the aquiclude is present. So this confined aquifer, it is between this aquitard and aquiclude. So confined aquifer, a water bearing subsurface stratum that is bounded above and below by formation of impermeable or relatively impermeable soil or rock, also known as Artesian aquifer. So you can see here this confined aquifer, it is bounded between the two surfaces here. Now let's have the look at the properties of the aquifer. Now the aquifer properties are associated mostly porosity, specific yield, then specific retention, storage by efficiency, field capacity, permeability, and transmissibility. First one is the porosity. Porosity or void fraction is a measure of the void or empty spaces in a material and is a fraction of a volume of voids over the total volume between 0 to 1 or as a percentage 0 to 100. Porosity of surface soil typically decreases as the particle size increases. Okay, you can find a greater porosity is there, but if the voids are more, okay, and if it is filled with the particles, you can see it is having the less porous soil. Specific yield, the quantity of water which a unit of volume of aquifer after being saturated will yield by gravity. It is expressed either as a ratio or as a percentage of volume of a aquifer. Specific yield is a measure of water available to wells. So you can see for different soil the specific yield is different. So for the gravel, for fine sand, for the clay, the specific yield is different. So it's because of the pores which are present between these layers. So you can see if the water is moving in the downward direction. So for the gravel, because of this specific yield will be more because of the rapid drainage of the water. Okay, it will be moderate in case of the fine sands, and it will be less as it is impermeable layer in case of the clay soils. So there is a slow or almost no drainage is there. Field capacity. Field capacity is the amount of soil moisture or water content held in the soil after excess water has drained away. The physical definition of field capacity is the bulk water content retained in the soil. So when the water, you can say the excess water goes away and the moisture is present in the soil, held by the soil particles, that is called as a field capacity. Okay, here the figure has been shown here, the soil particles and the water which are present between this soil. Specific retention. The ratio of volume of water that a given body of rock or soil will hold against the pull of gravity to the volume of the body itself. It is usually expressed as a percentage. Okay, now we will see what is permeability. Just as the porosity of a soil affects how much water it can hold, it also affects how quickly the water can flow through the soil. So that is a permeability. The ability of the water to flow through the soil is referred to as a soil's permeability. Now you can see that permeability of the water is depends again upon the types of soil. The example is shown here. Okay. So for gravel, sand, silt, clay, suppose the water is to be passed through that for a 1 meter depth. So it is possible that through a gravel it may pass through that because of the permeability present in the 2 minutes. Then depending upon the pores which are present in the sandy soil, it may take 2 hours. For the silt, almost there are very less pores, so it may take 200 days, and it may take several years in the clay soil because of the cohesive nature of the soil. Transmissibility, a measure of the ratio of response amplitude of the system in a steady state forced vibration to the excitation amplitude. The ratio may be in the forces, displacements, velocities and acceleration. The transmissibility of an unconfined aquifer depends upon the depth of groundwater table. Okay, here important thing is that it depends upon the vibration or steady state force vibrations of amplitude and transmissibility of any aquifer or any soil, you can say. So that depends upon the how much, for what depth the water table is present. Aquiclude, it is a solid impermeable area underlying or overlying an aquifer. So you can see here this aquiclude at present it is underlying the confined aquifer at bottom here, right? If the impermeable area overlies the aquifer, pressure could cause it to become confined aquifer. A solid impermeable area underlying or overlying an aquifer, it can absorb the water but cannot transmit it in significant amount. Aquifers, an impermeable body of rock which contains no interconnected openings or interstices, and therefore neither absorbs the water or not transmits the water, that is called as aquifers. And aquitard, you can say, a bed of low permeability adjacent to an aquifer may serve as a storage unit for a groundwater, although it does not yield water readily. So here you can in this cross section, right from the subsurface soil, followed by unconfined aquifer, followed by aquitard, then unconfined aquifer, again followed by the confined bed or aquiclude, then confined or phreatic or artesian aquifer is shown here, and which is followed by a confined bed or which is called as a aquiclude. So there are various theories which are developed based on the flow through the soils. So various scientists have worked on that. So one of the very famous scientists, which is Darcy, he created the equation to show the how the water flow take place. Further, again some work carried by the Dupuit, scientist Dupuit, so which has also carried out some based on his assumptions. So these theories are based on some assumptions. So let's see these what equations tells us. So Darcy, the scientist, the Darcy's law is a simple proportional relationship between instantaneous discharge rate through a porous medium, the viscosity of the fluid and the pressure drop over a given distance. Darcy's law is only valid for a slow or a viscous flow. Here you can see this particular. So Q is equal to K into A into I. Okay. So here again you may can Q is equal to K into A, where this I, which is a hydraulic gradient, can be represented by HL by L. Okay. So HL by L is nothing but the hydraulic gradient. A is the cross sectional area. K is the coefficient of permeability or transmissibility of the aquifer. Now if you see this particular soil portion, if it is there and this water has to pass through this, right? So here, right from this particular surface, so the water head present here and water head present, there is a difference in that, right? So that is called as a head loss. Okay. What is L? It is the length of that particular medium or porous medium, what is there present there. So HL by L, that represents the hydraulic gradient. Okay, K is the coefficient of permeability and A is the area of that particular medium, cross sectional area of that medium. So Darcy's law held for the very flow, which is a slow flow, you can say. Typically, any flow with a Reynolds number less than 1 is a clearly laminar, and it would be valid to apply Darcy's law, right? So that Reynolds number is rho into V into D divided by mu, where rho is the density of water, units of mass per volume, V is the specific discharge, not the pore velocity, with units of length per time. D30 is the representative grain diameter. So actually here, for a porous media often taken as a 30% of passing size from a grain size analysis using sieves with the using units of length. Now you are aware with the sieve analysis, how the highest and highest code specifies and what are the sieves. So mu is the viscosity of the fluid. Now again one more scientist which has given the theory, which is a Dupuit's. For unconfined groundwater flow, Dupuit developed a theory based on various assumptions. First one is a stabilized drawdown, that is the pumping has been continued for a sufficiently long time at a constant rate so that the equilibrium stage of steady flow conditions have been reached. Second, the aquifer is homogeneous, isotropic, of infinite areal extent and of constant thickness, that is constant permeability. Complete penetration of the well with a complete screening of the aquifer thickness with 100% well efficiency. Flow lines are radial and horizontal, and the flow is laminar, that is the Darcy's law is applicable. The well is infinitely small with negligible storage, and all the pumped water comes from the aquifer. So if you see the pumping test, so in the figure you can find in the aquifer this open well is there. This is a pump which is provided, or it is called a test well, and it is connected, this pump is connected with the controlling device, right? Sampling tap is also provided there, flow meter is observed, and also the settlement tank is provided, and followed by the discharge pipe network. Okay, some observation wells are also provided there. So what is pumping test? The water level in the well is depressed to an amount equal to the safe working head for the subsoil The water level is kept constant by making the pumping rate equal to the percolation in the well. So this is very important, that the water you are extracted in the pumping rate, in the pumping, that rate should be equal to the water that will come to the that particular well. The quantity of water pumped in a known time gives an idea of the probable yield of the well of the given diameter. This test may be carried out in an existing open well. So what is important here? Rate of seepage into the well, that is equal to this subtraction. What is subtraction? Volume of water pumped out minus volume of stored in the well, volume of water stored in the well, and divided by the time of pumping. So that is the seepage, rate of seepage. So it has also some this pumping test also having some assumptions. What are the assumptions? First one, the aquifer is homogeneous, which follows the Darcy's law. Darcy's law is valid. The flow is horizontal. The well penetrates the entire thickness of the aquifer. Natural groundwater regime remains constant with the time, and Dupit's theory is valid, that is that I is equal to dz by dr. So here all the these assumptions which are used by Dupit's theory are also applicable in the pumping test as well. So thank you very much for joining this session. In coming session also will deal with the various aspects which are associated with the groundwater hydrology.